this is what's going to produce the back current. So we end up with a reduced current. In essence, what the inductor does is it slows down the rate at which current increases. Without it, if I just took a battery and I hooked a wire from one end to the other, that current's going to be flowing through pretty quickly. So that graph would, if I did a current coming out of the power supply the first time, if it's just for a simple power supply, it would be very quickly get up to some value. But I throw an inductor in there, and this would be this is with a DC with an inductor. And typically from a manufacturing point of view, inductors are useful in the fact that if there's a power outage, it reduces the rate at which the current is changing, which means that you don't get the rapid change in current, so you don't get the rapid change in the magnetic flux, which means you, in essence, prevent things from, well, producing lightning in the lab. You got multi-million-dollar equipment, you don't want a spark suddenly shooting across because you've created a dangerous situation because you did not slow down the current in the power outage. All right. So our formula for the EMF across an inductor, for the voltage across an inductor, is negative L, change in the current over change in time. So now,
Is that a negative sign from the L?
pardon?
Did you put a negative sign from the L?
Yes.
Okay.
The symbol for an inductor is a curl. So resistor, it's the jagged lines. Capacitor, it's the two parallel lines. This, we got curls. I know the voltage for the power supply minus the voltage across the inductor is going to be equal to 0. VVS minus, the minus sign, I know I have a minus sign over there, I'm taking the minus sign already into account, so minus L delta I over delta T is equal to 0. And so this was big V sub n sine omega t would be equal to L delta I over delta t. Divide by L, and we get Vm over L is equal to sine times sine omega t is equal to delta I over delta t. Let's make sure I didn't screw up the minus sign. Nope, I'm good. So if I have a sine curve here, let's go back to our loop, preferably with a darker color here. So if we started out with cosine, that becomes negative sine. When we do slope, slope of that is negative cosine. Slope of that is sine. Slope of that is back to cosine. Except now I'm trying to find my current, and I know the slope of current is equal to sine. If the slope of current is sine, what is current?
Negative cosine.
Yes. So if I plotted those, so my voltage was a sine curve. That's voltage. My current across my inductor, or going through the inductor is a negative cosine. Voltage is leading the inductance now by pi over 2. And so we have the final rule in terms of leading and lagging, that current across an inductor lags voltage across the inductor by pi over 2, or the voltage across the inductor leads current by pi over 2. Now you get into a situation, you're suddenly going, all right, which one leads, which one lags? I can't quite remember. Fortunately, a student clued me into a memory trick here. Eli the Iceman. It works for me. Now, do recognize that an EMF is sort of an ideal voltage, generally represented by an epsilon. However, textbooks, when you're printing out a textbook, writing an epsilon is not necessarily simple to do. Back when, it's not like you just go into change the font. It was more complicated when you're printing a book 100 years ago. And so there are a number of textbooks that just use a capital E for voltage instead of epsilon or V. Not that it's confusing with energy or anything like that. So if you think of E as an EMF, so for an inductor, the EMF leads the current. For capacitance, the current leads the EMF. If that doesn't work for you, come up with your memory trick. So we have time, plenty of time, we got 3 minutes. An RLC series, wait, was that a series circuit in the?
Yep.
All right, RLC parallel circuit. RLC parallel circuit. Oh. Plenty of time, negative time. All right, set up my phasors. So, wait, that was parallel, I want series. No, I want parallel, I was right that time. That's what happens when I feel rushed. So I got my power supply here, I've got R, I got C, I got L. What's going to be common to all three of them?
Voltage.
So that's my voltage for the power supply, that's equal to the voltage across the resistor, which is equal to the voltage across the capacitor, voltage across the inductor. The current for the resistor goes where? Yep, they are in phase. The current for the capacitor.
Second quadrant.
Yep. The current for the inductor. I do not know which is bigger, IL or IC, I just pick one. Just without numbers, just conceptually, these are in opposite directions, just like the way I drew it. I know the current coming out of the power supply is the sum of the current across here, here, and here. So I'm going to be adding the currents. So I need to add these three phasors. Well, these two phasors are in opposite directions, so the sum is just the difference between the values because they're in opposite directions. So I have, this would be IC minus IL. It does not matter in terms of the math that we're about to do, whether IC is bigger or IL is bigger. If IL is bigger, the arrow should have pointed the other way, but it's going to wash out because we're about to square it, because I'm adding the current to it. That would be IPS. So I know that I of the power supply squared is equal to I from the resistor squared plus IC minus IL squared. This is V over Z squared is equal to V over R squared thus v over x sub c squared, x sub c minus v over x of L squared. And these cancel out, and the math is similar to what we did before. One other thing I'm going to throw at you quickly. When we found I here, we were finding what would produce this slope. So I, Vm over L negative cosine omega t, but when I do the slopes, the omega comes out, but the omega's not here, so we stick an omega down here to basically cancel out the omega when we take the slope. There are videos where I go into more detail. Matter of fact, the very first video I made, and it will seem a lot cruder than the others, which is saying something, is one of these videos. You can tell what we were doing right when lockdown hit. So, I know that for this, I is equal to V over L omega. And so V is equal to I times L omega. So my inductive reactance is equal to L omega. Those are all the pieces. I'm sure as you walk home tonight or drive home today, it will all click and you know, you didn't even need to bother saying any of it. It makes so much sense. And on that note, have a wonderful day.
Did you decide on the test was gonna be?
Why don't we make the test on Tuesday? Unless somebody wants it Thursday. This is the multiple choice test.
And this master set, can you do tomorrow or Thursday?
Thursday.
And master set 28.
Ask me on Thursday.